I would like to thank the organizers for the invitation. So I have known Frank for many years, and I was very happy when I was invited to this conference. And I'm very happy to be here, just to, for this occasion. Okay, so I'm going to talk about something which is not new. Okay, so if you have heard it, and then we have just had a big lunch, so you can just take a nap. Okay, and use this opportunity, and then we have some very exciting talk after me. So just get refreshed. Okay, so now, so I have been working on water wave equation for a long time, and so what I really want to say in this talk is the equation has very rich structure, and seems to be really there's endless of things to explore with this equation. Okay, and this is what I'm going to talk about is just one small aspect of it. Okay, so the equation we're going to look at is think about the wave in ocean, right? And we actually neglect the motion of the air. So the air density is 0, and the fluid density is 1, and there's a gravity, non-zero gravity. And we assume the fluid is inviscid, incompressible, and irrotational. And we also assume that the surface tension is 0. Okay, so the interface so the fluid domain is omega t, and which is moved with time, and the interface is the boundary. So that's just a notation. Okay, so we know that the motion is described by the Euler equation with gravity. Okay, and this p is pressure, v is velocity, and incompressible, divergence is 0, and irrotational curl is 0. Okay, and the pressure is 0 on the interface. Okay, and the last statement is that the particle on the boundary remain on the boundary for all time. Okay, stay on the boundary. Okay, so now there is a very important condition associated with this problem. So in particular when surface tension is 0, which is the Taylor sign condition. So basically it requires that the pressure should be increasing in the inward direction. Okay, inward normal direction. And this condition was proposed by G.I. Taylor in 1949, and basically so if you can make this condition strong if you put a positive lower bound to it. Okay, so there's a long history to this problem, right? So really many people studied it. And so here I'm just going to review something very recent, just a small aspect of it. So it's the so-called local well-posedness, in particular in Sobolev spaces. So the first work was given by Nalimov, and then Yoshihara and Watercraig. So what they did is for 2D, so that means the interface is 1D, okay? And the local well-posedness, so in small, for small Sobolev data. So the data in Sobolev space is small, then you can solve it for short time. And so in the case of Nalimov, there's no bottom, and in Yoshihara, there is a bottom that do not interact with the interface. Okay, there's a positive distance to the interface. And then we were able to show actually the Taylor sign condition always hold for the case which is infinite depths. Okay, there's no bottom. And because it's always hold, and we are able to show that actually the equations locally were posed for arbitrary data, including the data that is like, the overturns. Okay, and that's the interface needs to be smooth, sufficiently smooth. And this work has been extended to many directions. So this is really just a small subset of it. And I would like to mention the work of Christodo Lingbar, okay, where they did, when they can allow that the vorticity is not 0. And then we also have Ambrose Masmoudi with surface tension, and Davilan with finite depths, okay, but and many other people, okay. So these are all local well-posedness, but then in all these situations, the Taylor sign condition do not necessarily hold, okay. But in fact, in the case of Davilan, he's able to show if the bottom is a small perturbation of the flat, and then it still holds, okay, and then basically you have to assume the Taylor sign condition hold, okay. Okay, then we also know there's also quite a few work on global in-time behavior, but for small localized data. Okay, so in the same direction of Daniel Tataru talked about this morning. So for 2D case, it's like really the time decays t to the minus 1/2. Okay, so in 3D, the decay rate is t to the minus 1. So for 3D, we were able to show that the water wave equation is well posed globally for small and the smooth localized data. And German Masmoudi Shatar give a different proof, and also furthermore they showed there's a scattering. Okay, and Ionescu, Pizzateri, Al-Azhar, Delors proved global existence and modified scattering for the 2D case. So as 2D case, it's t to the minus 1/2. So what we did was actually, I mean, if you don't do any further work, we only can show that e to the almost global, it's e to the 1/epsilon. Okay, so some further analysis in this work is just prove using modified scattering, they can push the time to global. And Ifrin, Tataru, and their collaborators were able to lower the regularity threshold. Okay, so now in all this work, the global existence result, there are two main ideas. So what's interesting is that the water wave equation, after a suitable change of coordinates and variables, and the quadratic nonlinear term can be just completely transformed away. Okay, so essentially you are dealing with an equation with only cubic nonlinearity, and then so if you do not use dispersive decay, then you can show that if data is smooth of size epsilon and not necessarily localized, then the solution exists for time of epsilon minus 2, right? Because this was rated cubic. But if you also use the decay property, then you can, for the 2D case, it gives you almost global. But if you use modified scattering, it gives you global. Okay, so in 3D case, and if the quadratic nonlinearity can be transformed away with time decay minus 1, then you go to global. Okay, so the main mechanism here is that essentially there's no three-wave resonant interaction in the water wave. Okay, so now the question is whether we can further remove the cubic nonlinearity, right? So maybe, okay, so there's a long history started with Zakharov to look at this problem. Okay, so you just look at the resonant interaction. Okay, so in this work of Dyachenko Zakharov, so they look at the periodic water wave problem from Hamiltonian point of view, and they find there's like no three-wave interactions, but there are four-wave interactions. Okay, and what's amazing is that the interaction coefficient vanish on the non-trivial resonant manifold. Okay, so there are trivial resonant interactions, but the non-trivial ones just disappear. Okay, and then in the Craig and his collaborators, they will try to make this result rigorous. Okay, and then it was actually the first work was actually making it really rigorous was Berti, Fiola, Pizzateri, and they were able to show that for data of size small, smooth, of size epsilon in the periodic case, they can solve the equation to order epsilon minus 3. Okay, so what do we mean by there's no the work of Dyachenko Zakharov? Okay, so this is like, so there's no three-wave resonant interaction, and then they, after some Birkhoff normal form procedure, you can write Hamiltonian system like this. Okay, like doing some Taylor expansion. So so there's no H3, right? So for the four-wave interaction, there is a trivial one, and then there's also Benjamin Fair resonance. And they can show that there's no cancellations on the trivial ones, and the coefficients on the Benjamin Fair resonance just disappears. Okay, so basically this result says that, well, in short, straightforwardly, you cannot transform away the cubic nonlinearity because there's trivial resonance, four-way resonance. Okay, but the method of Birkhoff normal form actually works very well with the trivial resonance. So this is really the main idea of Berti, Fiola, Pusateri. So they constructed bounded invertible Birkhoff normal forms, but and then they were able to show for data of size epsilon, the existence is epsilon minus 3. Okay, so the construction is based on several like pseudo differential flows, conjugating several pseudo differential flows. It's not explicit. Okay. Okay, so now the question we really want to investigate is that, well, so these constructions it's always on the Fourier side and sometimes not so explicit. So we want to understand what really is going on in the physical side, right? Because the Euler equation is written in the physical space. What is really going on in the physical side? So straightforwardly, the cubic nonlinearity is still there, but maybe in some sense and can actually disappear. Okay, so what do we mean by this? No non-trivial resonance. Okay. Okay, so how do we usually solve the water wave equation? And because it's a divergence zero, curl equals 0 means that the velocity field is a harmonic, a holomorphic. Okay, harmonic, so it satisfies harmonic equation. So this means we only need to know the velocity on the interface, and then you can solve it back inside the Fourier domain. So this is really a classical approach, just to reduce the problem on the interface, so that therefore you don't have to deal with the free boundary, right? So the bound, okay. Okay, so here, I give a brief derivation on the interface. So we identify this is 2D case. So we identify the point xy with its complex form, okay? And the free interface, this alpha is Lagrangian coordinate. So this means if I take derivative to t, I will get the velocity. So alpha is describe the same particle. And if I take 2 derivative to t, I will get acceleration, okay? And now the gravity is just, so normalize the gravity to be 1, then it's 0 minus 1 is just minus I, okay? So gradient P, pressure 0 on the interface, so gradient P points normal direction. So if you do a decomposition in the tangent and normal direction, there's only normal direction survive. And we write it as IA z alpha, because z derivative to alpha is a tangent direction, right? So you multiply I, you get normal. And then you get, like, its A is a real valued function. It depends on negative dpdn, okay? So this is the zt bar is a boundary value of a holomorphic function, because the v bar is holomorphic because its divergence curl equals 0, okay? So we have zt bar is holomorphic, boundary value holomorphic. So this is a water wave equation. And now if you write equation on the free interface, you just translate this completely into the free interface. So the left-hand side is acceleration. So this is like acceleration, right, on the free particle on the interface. So this is a gravity, and the gravity now is on the right-hand side. It's become plus I. And negative gradient P is IA z alpha, right? Big points only in the normal direction. And divergence curl equals 0 means V bar is holomorphic. So it just satisfies a Cauchy integral formula. So this is really the holomorphic function satisfies Cauchy integral formula. And this is the Hilbert transform on the interface. Okay, so there should be a principal value here. Okay, so it's like twice of the Cauchy integral. Okay, okay. So now, of course, if we look at here, it's a little bit difficult to understand because the unknown that which is the interface is in the denominator. So this is why we want to use Riemann mapping coordinate. Okay. So the Riemann mapping takes the lower half plane to the fluid interface. Okay. So that's a Riemann mapping. Okay. And this is just a normalization condition. We assume that the derivative to z goes to 1 at infinity. Okay. So now just straightforwardly, the Riemann mapping takes a boundary to boundary, right? take the real line to the fluid interface. So now the fluid interface can also be described by this, the Riemann mapping evaluate on the interface, on alpha prime is a real number in the low half plane. Okay, so it's just boundary of the real half plane. Okay, but in between this one and the Lagrangian coordinates, there's a change of variable, right? So we just use h to denote the change of variable. So z evaluate on h just equal to the Lagrangian coordinate. Okay, so the Riemann mapping variable we write as capital H z, and the Lagrangian coordinate we write little z. Okay, so and then this here is just a notation. Capital ZT still describes the velocity. Okay, so this now is given by the material derivative. Material derivative means that you take a derivative in the you know, along the fluid particle. Okay, so in the you just follow the same fluid particle. Okay, capital DT, and then there is a change of coordinates just coming from there is a b. This is like from the chain rule. Okay, so you have, these are just notations. Okay, capital ZTT is acceleration. So now the fluid interface on the fluid equation on the interface is just written, it's the same way, right? So this acceleration minus the gravity and equal to the right hand side. So instead of writing IA z alpha, I write some real value function A1 divided by z alpha bar, but 1 over z alpha bar points in the same direction as capital Z alpha, right? Because z alpha bar times z alpha is a real number. Okay, so this is like this, and then to be holomorphic, ZT bar is holomorphic means that I minus the Hilbert transform. This is a flat Hilbert transform here. Okay, so the advantage of using Riemann mapping is now the Hilbert transform is really just explicit like this, right? So it's very simple. So I minus h of zh bar equals 0, and also 1 over z alpha. So 1 over z alpha is really z. Remember, z alpha is the boundary value of the Riemann mapping, right? So you take derivative to alpha means that it's really the Riemann mapping. You take derivative to the z, okay, phi z. So that's still a holomorphic function, and the 1 over z alpha, that's a boundary value of holomorphic function, and which goes to 1 at infinity. So I have to subtract 1. So this function goes to 0 at infinity. So I minus h applied to this equal to 0. So we were able to derive this formula that was many years ago. Okay, so I don't want to say how many years ago now. So so many years ago. So this. Okay, so we have that actually A1 is 1 minus imaginary part of this commutator. Okay, so this commutator you can just expand it. You find this quantity is always non-negative, so that means A1 is always greater than or equal to 1. Okay, so and this B also have a exact formula. So precisely up to by here, we are able to actually really say that negative dpdn has to be non-negative, right? Because this is how you would write negative dpdn. After all these change of notations, you just follow the notation minus 1 over z alpha absolute value times dpdn just equal to A1, which has a positive greater than or equal to 1. So that means negative dpdn has to be non-negative. Okay, so this was the proof. Many years ago. Okay, so now, so now there was also but this equation. So by now this is like really a closed equation, and the problem is we still cannot solve it because it's fully nonlinear. Okay, so it turns out that if you just take one more time derivative to the first equation here, the Euler equation, you get a quasi-linear equation. Okay, so I go back to the Lagrangian coordinate. Okay, just take one time derivative and you get, so you take one time derivative to this equation, right, to this equation, you have capital Z, little t, z t t t, right, this is like 2 times I a z t alpha plus I a t z alpha, okay, and this is the left-hand side, right? So this is a higher order term, this is a lower order. So now I also put a bar to everything on this equation. So the left-hand side is higher order term, the right-hand side lower order term. And the reason is, a simple reason is that if you look at this equation, so the t bar is holomorphic, right? So this means that if you take derivative, you no longer get holomorphic, but it's still close to being holomorphic. And you apply some derivative, it's still being holomorphic. So left-hand side is being almost holomorphic, close to being holomorphic. But the right-hand side, if you just remove the bar, it's IAT Z alpha, it's really just point in the normal direction. So a holomorphic function on the boundary only points in the normal direction. That means that it's zero, right? So you cannot have holomorphic function which have tangent direction equals zero. Okay, but now because the left-hand side is not exactly holomorphic, so the right-hand side is lower order term. So this is based, and also if you look at the IA d alpha, so I d alpha is applied to the holomorphic function. This is really the Dirichlet-Neumann operator, which is a non-negative operator. Okay, it's a positive operator. So, and A is associated with the Taylor sign condition, right? It's non-negative. We have just proved, or positive. So this means that this is dt squared, this is, and then plus a positive operator. So the whole thing looked like a wave type equation, right? So this is why we were able to prove local well-postedness of this equation. So writing in the Riemann mapping variable, you would have this form. Okay, so this is right-hand side, and we do have a formula for this quantity on the right-hand side, which is you can write it down explicitly, and it's a lower order term. And the key point here is by now we only know it's quadratic. Okay, so of course it's a nonlinear equation. There are quadratic nonlinear terms. Okay, so the main equation of the water wave will look like this. Okay, so the main operator here applies to the velocity equal to some quadratic lower order terms. So if we just look at this equation for initial data of size epsilon, you can solve for time epsilon to the -1. So how do you go to the epsilon -2? Okay, so it turns out there's some very simple transformation. Okay, so this is what we find. So if we look at the velocity potential, okay, so that means v equal to gradient phi. So we look at the boundary value, the evaluation of the trace of the velocity potential on the interface. Okay, so if you look at this quantity, and this H is a Hilbert transform, right? So you project this quantity to the space of holomorphic functions in the air region. Okay, and you also project, so z minus z bar is the height only, right? So because there's an imaginary part of z. Okay, so it's only the height of the interface. You also project the height of the interface to the holomorphic functions in the air region, and turns out these two quantities actually satisfy equation of this form, right? So it's the same operator, right? So it's dt squared minus a. So the reason there's a minus, not a plus, because these quantity would be anti-holomorphic in the water region. Okay, so remember our main operator look like this, right? So this is like this operator acting on holomorphic, right? So now if it acts on anti-holomorphic thing, it's a minus. This main operator acting on these two quantity, you result something on the right-hand side is just cubic. There's no quadratic term, it's cubic. Okay, okay, so now this A is a nonlinear term, right? So there's still quadratic nonlinear term on the left-hand side, but then you just do a change of coordinates. Okay, so it's like twice of the real part of the interface minus h. So instead of taking the Riemann mapping, but you reflect the Riemann mapping across a diagonal. Okay, so then you find that if you use this change of coordinates, you will get the equation look like this. Okay, so this is actually exact. Okay, so it's precise. So this negative I minus a d alpha becomes like dt minus I d alpha, right? So this is like, it's like linear, and plus acting on this new transformed the quantity in the new coordinate system becomes something cubic, and this is cubic. Okay, so the quadratic nonlinear term can just be completely removed. Okay, so and then, well, so this is a natural energy functional associated with the equation like this. Okay, so one of the energy functional. So if you so because there's no quadratic nonlinear term, so if you can just take as many derivatives as you want. This is like this derivative is really just any derivative. It can be just dx, can be dt, and then can also be vector fields, right? So you can just take derivative, and then you plug into the equation, and then you take this energy function d dt will be a quartic term, okay? And same for this. So this is like, so if you only apply derivative in the spatial direction dx, then you will get existence of solution for time of order epsilon minus 2 for data of size epsilon, right? But if you, of course, if you apply also the vector fields, right? So we use a vector field method, okay? So this naturally gives us time decay, okay? And then you will be able to solve time almost global, okay? So and then now this similar quartic estimate also play key roles in the work of Ionescu-Sateri, Alazar Delors, and Hunter Ephraim Tataru. Okay, so the real new, but as I mentioned earlier, that there were the modified scattering were introduced in this work to really just go all the way to global. Okay, so now the main mechanism behind what I have been talking about is really just the absence of no three-wave interaction, right? So that kills the quadratic nonlinear term. Okay, so now the question is, can we go further? Okay, so since this energy equality is so important, so can you just make this side quintic? Okay, so can you make this side quintic? So this naive idea is like you really just take all the quartic terms and then try to find the antiderivative, right, and move to the left hand.
So you renormalize things and you put it on the left hand side.
Yeah, you try to put things on the left hand side, right? You try to identify things and put on the left hand side, quartic thing. So you just naively, if you keep doing it, then you were able to close your argument. But there is something unfortunate with the earlier work is that, well, we never thought about going so far. So what we construct here was not so easy to identify how to go backwards, right? So if you just think about what you have to do, say, suppose you have a quantity like, so what will be the antiderivative of something like this, right? The product of 4. But so if you go forward direction, if you take derivative of this, you will have like and then when you have derivative 4 on the second term, and you have the derivative 4 on the third term. Right. So that means if you want to find the antiderivative of something, they have to come at least in groups of 4, right? Then you can move backwards. If they don't come like, if they don't have something like this, then you cannot move to the back, right? So this means that the right-hand side should exhibit this kind of symmetry, okay? Otherwise, you won't be able to find the antiderivative. But in the early, if you just look at this way, you won't be able to, at least it wasn't clear to me how to do it, okay? So this means that we have to rework out the previous work, redo the previous work, and to make it symmetric, okay? So that was really the main idea, okay? So just to make it symmetric, and doing things symmetric, and then try to identify all the symmetric structures, and to make things as symmetric as possible, and then you trace it back. Okay. So it turns out what works is the following. Okay, so this is just a choice we made because we know that once you are in the Riemann mapping coordinates, at least the Hilbert transform is much easier. Okay, so it's just like the structure is more explicit if you in the Riemann mapping coordinates. So this is notation. So this is a projection into the space holomorphic function in the lower half plane, and this is in the upper half plane. Okay. So we start with this same quantity, actually a similar quantity, not the same, but similar. So this is I plus h of the velocity potential, but composed with Riemann mapping coordinates. So you see this, the reason we choose this is because here we know that this works. Okay, this is a good quantity which you apply by this main operator, you get something cubic. Okay, but if you don't want to do this in the Riemann mapping coordinate, so you take a projection and then you do this in the Riemann mapping coordinate. So that's the corresponding quantity in the Riemann mapping variable. Okay. Okay, so now it turns out after several try, and we find that the main operator is this one. Okay, so this is still the material derivative, but this time we are not. So let me just review the main operator here. So the main operator here should be dt squared plus or minus ia d alpha, right? So you take two material derivative, and there is this Taylor sign negative dpdn in here. But what really worked here is that you take material derivative, but then you take a projection to the space of holomorphic function in the lower half plane, then you take material derivative again. But here it's just 1 over capital Z alpha square, and you are not really using the full A1, right? So the coordinate, in the Riemann mapping coordinate, it should be A1, right? But this A1 disappears. So you see, so the operator should be like this if you don't, I mean, straightforwardly, right? But you don't do this. It's like you take material derivative, you take projection, you take material derivative again. And here this A1 is 1 plus something positive, right? Commutator disappear, it's just 1 over the alpha square, okay? So this is, and the right-hand side also become much simpler, okay? If you apply this operator to this quantity, the right-hand side is just like, so it's something purely anti-holomorphic because PA, right? PA is a holomorphic, anti-holomorphic, acting on this quadratic nonlinear term. Okay, so it's like this is like something holomorphic, right? Q is holomorphic. After being applied by this operator becomes something purely anti-holomorphic. Okay. Okay, so this is like, turns out to be a good starting point for several reasons. So, and it also turns out that, so we want to construct a sequence energy functional that involves all derivatives, all orders of derivative, right? So now you just keep taking, so this is the first quantity, and then you keep taking material derivative. Every time you take material derivative, you project and then keep doing it, okay, j times. Okay, so this is a sequence of quantity, and this same operator acting on that, and then we just, this is a notation we call gj, okay. So the first one, what's important, the first one is just in the holomorphic sense is 0. Okay, so the left-hand side is something almost holomorphic. The right-hand side is anti-holomorphic. So this is already some extra cancellation involved, right? Because, okay, so that means both sides should be something 0. Okay, okay. So the right-hand side take projection to the holomorphic is 0. Okay, then we will also be able to derive a formula for this right-hand side in the holomorphic. After holomorphic projection, that it has a nice symmetric structure. Okay, so in other words, we're able to put things symmetric enough to find to do this process. Okay. Okay, so another key elements involved is this energy identity. Okay, so this is a new energy functional different from the previous one, right? So in other words, if you look at this energy, that also look quite symmetric, right? So if you have two holomorphic quantities, and this I d alpha of the projection and the material derivative of the first one, and then you do this, okay? And turns out the E dt just equal to this. So this is one important reason why this operator is involved, right? So this operator, again, is like naturally involved with this energy identity. Okay, so this is operator, and then this just a notation. Okay, Okay, so with all these together, so we just apply this energy identity to this sequence of quantities qj, right? So we just apply to them. We apply to qj and the qj plus 1. Okay, so you apply. So theta 1 is qj, theta 2 is qj plus 1. So this is like qj plus 1, qj plus 1, and then there's qj plus 2, right? So this is qj plus theta j plus 2. Okay, so apply the energy identity, you get dEj dt just equal to this. Okay, and we are able to derive this recursive formula. So this recursive formula exhibits some very nice symmetry. Okay, so this is notation. So this bracket is defined as the following. It's something really symmetric, like f alpha minus f beta, g alpha minus g beta, h alpha minus h beta. It's symmetric, okay? And then this is bracket of this. So this pH, you can really, if you look at this thing, so you plug in here, right? So you have this bracket, but you have 1 over z alpha. But what is 1 over z alpha? So you can remove this pH, right? Because theta j plus 1 is holomorphic. And then you put the bar over here. This is anti-holomorphic, right? So you look at, you just put a minus here, okay? So this is only so this means that you can because the holomorphic part, integral of something holomorphic indicate infinity 0, right? By Cauchy integral formula. So that means we can actually remove this pH. So 1 over z alpha combined with this, it's again that's d alpha theta j, capital D alpha theta j, right? So you have something really look symmetric. Why this is symmetric? Because what is zt? So zt is velocity. So what is I 1 over z alpha? So I of 1 over z alpha, I times 1 over z alpha is really like one more derivative to zt, right? So the acceleration, ztt, okay? Plus something quadratic, which we like because it's already put us into quintic. Okay, so it's ztt. So and also what is capital D alpha zt? So capital D alpha of something is 1 over z alpha of derivative d alpha theta k, right? So this quantity you can also check. It's like really k times material derivative of the velocity zt. Okay, so this is exactly, so if you look at plugging this, so you have j plus 1 time derivative, and you have 0 derivative, and you have 1 derivative, and you have L derivative to the same quantity z alpha. So you have different orders of derivatives in these 4 factors, right? So different orders, like, you just, okay. But and then you plug in, so you get a bunch of derivatives, different orders of material derivative to the same quantity, which is a velocity, okay? And everything else is symmetric. So in order to perform this finding the antiderivative, so you really, because you want to move the derivative around, right, to make it even out. You see, every time you take, if you have something like this, you need to have one derivative, one derivative, one derivative, one derivative, okay? So you have the same number of derivative you can. So we need one more thing which allows us to move this material derivative from factors to factor. So it turns out this thing works. So provided that this P is really the main water wave operator, okay, and we know that the main water wave operator acting on typical quantity give us something quadratic, okay. So we know that the quantity we involve always have this being quadratic. So assuming that these are quadratic, and then ddt of this thing just equal to twice of this plus something quintic. So if you look at right-hand side, it exactly give you, so these two terms look very similar, except that you have a dt here and then you have a dt here, or you have dt here. So in other words, the dt in the first term, which applied to q, is moved to the dt of the second term, which applied to h bar. So this thing allows us to move derivative to one factor to the other. Okay, so then you are able just to go backwards and then to move the derivative to the right place, and then eventually you will find. So you hopefully you will get. So so eventually, I mean, if you have something like it's really. So if it's really f to the fourth derivative, it will be 4 times f1 derivative f to the q, right? So if you end up with something this, you will be able to find its antiderivative. Okay. So and that's actually what we can just really achieve. Okay. So that's really what we can do eventually. So you move. I mean, things just really look like this eventually. Okay, so we make things symmetric. So we look at theta equal to zt bar alpha minus zt bar beta. And this capital dt involves both d alpha, d beta. This is just one way to make things symmetric, right? So you don't, it's as less messy as possible. So it turns out these are the characters, okay? So because this is the process of moving the derivative around among terms, and like you do things symmetric, and then eventually the middle term exactly look like this, and then you can find the antiderivative, right? So you don't want like 100 derivative 1 factor 90 to the second, right? So you hope you share the derivative, even them out, and then you get one antiderivative. Okay, so this is another group of characters. So all of these quadratic, Quartic. Okay, so then you have that. Now this is the original energy function node, and then these are the characters. You subtract these, and you take derivative to time. You get something quintic. Okay, so this is how much time do I have?
15 minutes left.
Okay, thank you. Okay, so we get quintic. Okay, so this is a remark. Okay. So this is remarkable. By putting things symmetric, we also find that the left-hand side actually really allows us to see the structure of the water wave better than we used to. Okay, so we find that this new energy function involves only spatial derivatives of these basic quantities, velocity, and there's a position. Okay, the reason is like the simple reason is really that here, what's involved, the typical term really just look like always f alpha minus f beta. So you only need to know the derivative, not f itself, just the derivative. Okay. So only involves derivatives of 1 over z alpha and zt. So this means that wave with large steepness and the large velocity can still be small in this energy function. Okay. And then d dt of this is also quintic in terms of the spatial derivative of these two. Okay. Then that means we can close argument. Okay. So now, of course,
derivatives you have to take. How many derivatives you have to take to do this?
That's a good question. How many? Actually, I didn't try to optimize it. Okay.
But you have to take higher and higher derivatives.
Not very high. Not very high.
No, to remove.
How many derivatives? So this sequence is j from 0, 1, 2, 3 to infinity.
Okay.
So this is like you have all orders of derivative. Yeah, you are
from a certain point. Yeah, okay.
No, you are able to just keep taking the form.
This I understood, but
yeah, this is just we are able to construct the sequence for all orders of derivatives.
Yeah, no, but in order to get to the quintic, you need a certain number of derivatives, I presume, right?
Need.
No, anyway, I don't want to interrupt.
No, actually, the lowest is easiest to work.
The lowest is easiest.
Yes, epsilon 0, right? Epsilon 0, you will get like you have to just go back to you involve exactly just one term. You involve exactly one term. It look like this. Okay. It's a higher like
so
you
take higher derivatives just for that.
The higher, then you have derivative in all places. Then you have to move them around, right? But the lowest is the simplest, and actually, this is why we were convinced that we can go, because the lowest.
You see it from
yeah, if you see it from lowest, you feel something's right. There's something interesting going on, right? So then you get the whole sequence. Okay. So the lowest is actually really just like this. Okay. So now this is just one of the analytic results that came out of this. And I don't know if, I haven't tried to milk other results out of it. Okay, so because this, I like this algebraic things better than this analytic things, but let me just state
No, that's good. Yeah, I totally agree. I totally agree.
Thank you. Okay, so yeah, I like the algebraic things better than the analytic things, but this analytic things is just one thing. I just try to say, okay, now this is something I can prove, okay, with this quintic identities, okay, energy identities. So this is a scaling law, okay. So we know that under this. So if that means if you rescale like this way, you still get the solution. So if z is a solution of the water wave equation, and then you just for arbitrary lambda positive, this rescale solution is still a solution of the water wave equation. Okay, so these, you can check that these are scaling invariant terms. Okay, so this is one spatial derivative in the Riemann mapping variable in L2 norm to the velocity on the boundary, and this is h dot 1/2 norm. Okay, and this, of course, this describes the steepness. Of course, it's also scaling invariant. Okay, so now this is L. Okay, so this quantity involves two orders of derivatives. So the first line is scaling invariant norms. The second line is just exactly one derivative about exactly one spatial derivative about the scaling. Okay, so it's not scaling invariant, but anyway, so this is L. Okay, now assuming the data is smooth enough, initial data is smooth enough, but we also assume that this quantity, this sum, the L0 is small enough. Okay, so this quantity is small initially, and this quantity just less than 1. It doesn't have to be small. It can be just very close to 1, but it's 1. Okay, less than 1. And then E1, E3 are just this energy functional I constructed a little earlier. So this is the first order, this is third order. Okay, I will explain why this is involved. Less than some universal constant m0 square. So this two just less than some universal constant, and this quantity is small, less than epsilon. Then the lifespan of the global classical solution, a unique classical solution for the 2D water wave, is at least of order epsilon minus 3. And during this time, the solutions as regular initial data and LT remain small. Okay, so maybe I didn't emphasize earlier. In fact, what I'm talking about here also work for the periodic case. So everything goes through. The extra thing is you just need to deal with some constant, which it's naturally come with periodic case, and then it's easily transformable, translatable. You can translate everything to periodic. Okay, so now instead of, I only assume the first line to be less than epsilon, so this second line can be arbitrarily large, okay, and this first line less than epsilon. If I only assume this scaling invariant quantity to be less than epsilon, but this is less than some universal constant, then you solve it slightly for some slightly shorter time. Okay, so this second result is really a cheap consequence of the first one. Okay, and during this time, the solution is regular. Okay, okay. So what's the main idea? So the main idea is really just use this quintic thing, right? So what is E1, E3? So E1 we can compute. Essentially, it's equivalent to, it's bounded above and below, okay, by these two quantities. So L2 norm of this and h dot 1/2 norm of this. So they have the same scale. And E3 is like exactly one derivative about this, right? Exactly one derivative about this. And then E1 times E3 is scaling invariant. And essentially, E1, E3 is involved is why we need E1 and E3, because we need to control 1 over z alpha minus 1, this quantity for a long time, epsilon minus 3. And we cannot do it directly because this quantity is not directly constructed in the sequence. Okay, so we use Sobolev embedding. We know this can be bounded by a universal constant time these three. Okay, okay. So this means that I'm able to control E1 and the E3 for time of order epsilon minus 3. Okay, so if I can control this for time epsilon minus 3, then I can control this for time epsilon minus 3. So this is exactly why I'm making assumption here. Okay, so essentially I really need this to be less than 1 for that much time. Okay, okay. So if this quantity is less than 1 subtract a little bit, then it remains 1 subtract a little bit for time of order epsilon minus 3. Thanks for the right hand side. Okay, E1 and E3. So this M0 is just a universal constant. So as long as I make sure that C0 times M0 squared is less than 1, I'm okay. So and delta can be arbitrarily close to 0. So that means, and we know this quantity controls the steepness. So this means that steepness can be arbitrarily large here. Okay. Okay. And also, okay, so now the part 2 is really just if you rescale the data, okay, you find this quantity of the rescaled quantity will have epsilon in front of it, right? So if you take epsilon small enough, even though initially it's not small, after some rescaling, you get something small. So if it's small, because it's small, we know we apply the first part. The rescaled solution exists for time epsilon minus 3. So you go back to your original variable, you go epsilon minus 5/2. Okay, this is why we lost a little bit of lifespan. And here, being requiring 1/z minus 1 less than 1 means that we can only deal with a graph. Okay, so this implies it has to be a graph. Okay, so the wave cannot overturn, but can have large steepness. So the main idea is really just use this quintic identities. So this we can check that these energy functionals we constructed exactly is equivalent to these homogeneous Sobolev norms. Okay, so this is okay for J's order, and then we actually used for J between 2 and 4. Okay, to just derive these results, but I don't think it is optimal, and I didn't try to make it optimal, like to make a smaller range or what. Okay, but because it becomes more technical if you try to make the range smaller. Okay, okay. So DDT of this will also have O epsilon 3 times this. So that means we are able to control all these terms for time of epsilon minus 3. Okay, provided initially if this is small, if this is less than 1 minus a little bit. Okay, some further remarks. So why are we doing this, right? So I actually by now I also, of course, I'm actually working on something else. Sometimes you wonder why you are doing this, but anyway. Okay, so I think at that time I was really curious that in the material space, in the physical space, how to visualize these cancellations, like no quartic resonance, no four-way round-trip resonance, right? It's actually I don't know if I wasn't even thinking that way. So anyway, so this structure comes out because I was working on something else. So it turns out that this similar calculation also applied to a variety of free boundary problems. Okay, and then we are able to use similar idea to derive some higher order derivative for integrability for cluster problems, and which we haven't written up. Okay, so I'm not giving details here, and I want to mention the recent work of Ionescu Sateri, and they obtained a similar quartic integrability result, and they also further use dispersal property and this quartic integrability to push the time existence to some epsilon minus, I don't remember, minus 8. Okay, I don't remember. Okay, so this is the new work. Okay, but the main idea is really the quartic integrability. Okay, but if you don't apply dispersive, you stay with epsilon minus 3, but you apply dispersive, you go longer. Okay, so Happy half birthday.
Thank you very much. Are there questions?
I have a silly question. So why do you get only epsilon to the -3 since you have, on the right-hand side, you have fifth order terms? You'd expect to get better. You'd expect to get
it's
to the -4.
It's quintic.
Quintic, right?
Yeah. So if that means that, if it's quintic, it's -3, right? So if it's if it's quartic, it's -2 because it's essentially we removed cubic nonlinearity.
Okay, so that's
in some sense. Yeah, if your equation don't have cubic nonlinearity, then you get naively you do energy estimate, you apply the equation to the solution ddt of this energy equal to something quintic, right? So
okay, so and the other question I had is with this E1, E3, this the product of energies, right? So that I found. Can you say a few words about?
Why?
That's strange. So
yeah, E1 times E3.
yeah, that you are using this product of energies.
Yes.
So which have different scalings, I presume. Right?
But the product is scaling invariant. It's the same scale. Yeah.
Right.
Yeah.
But so each one has different scales, and the product is scale invariant.
Yes. Yes. So it's essentially this is one way of controlling this.Maybe I don't need it. It may be, if you are able to control this.
Only for that reason.
Yeah, this is no, this is not. There's nothing, no deep physical reason, at least as far as I can see. So it's really because I want to control this, and I use this Sobolev embedding. Like you control one derivative, slightly below, slightly
so it's
above.
Really just an interpolation.
Nothing deep here. Yeah.
Okay.
But the reason is I'm able to control this, but I'm not able to control this.
Okay.
So
it's just interpolation.
yeah.
Okay. Just a question for the beginning. For short time, do you need z of t to be a graph?
Zeta t.
At the beginning to pole local existence.
No. The local existence can be just arbitrary.
And what about a bubble? It will work also?
It's also okay.
Okay.
Yeah.
It's just the Taylor.
Yeah, it's a Taylor. Yeah, as long as the Taylor sun condition hold, you can have bubble. What do you mean by
But then
bubble?
when you stretch, that's what
Yeah.
Yes. So can you do you think that you can repeat and go on?
Repeat forever?
Well, at least for some time.
You mean? Yeah, I tried. I tried. This is all embedded in this. You mean just make a quintic and even further, right?
Further, yeah. But at least the next step.
Yeah, the next step
If
I
you
tried.
succeed the next step, then you know it goes.
Unfortunately, the next step is not achievable. So I actually I do like
So you have
f to the
abstraction.
fifth.
You have abstraction.
Yeah. So there's only one term left, which is clearly not removable.
But so that's the interesting thing.
Hmm?
So it's an interesting thing.
Yes.
That's right. it's an interesting term, but I don't know how to make use of it yet. So yeah, it's the next step. No, I have to mention that it's not completely new, right? So there is the work of Craig Wolfach, and then Dyachenko Zakharov repeated later using different methods. They find that there are non-trivial five-way interactions. So using their framework. But still you can ask the question whether you can perform this energy function and remove further, right? Since we are, so I did manage to put things symmetric, and unfortunately there's only one term left, and which is not removable. There's no chance. I tried. Okay. Yeah. So I think that yes, even in this sense, you cannot go further.
Yeah, I had a kind of follow-up question to that actually. So I don't know the subject at all, but it felt like it was a bit of a trial and error method.
Yeah.
Is there a systematic way of, let's say, guessing what the energy would look like, and if there is not, then in the end, once you have the form of the EJs, you have some kind of interpretation of what they are and why those are good quantities?
That's a very good question. Actually, I try to do afterwards, right? So, I did this when I was younger. I have had, and I'm more enthusiastic. So every morning you wake up, you find, you just sit down and work, and then you find there's some new structure come out, and you keep working, right? So it's not completely trial and error. You do see structures there, okay, right? So it's actually my motivation of doing this was not because of, even though it looks like there's no four-wave interaction. Yeah, it is related to that, but I was doing something else, and then there's some interesting structure came out, and I thought I should explore, and then every day you have something more to explore, and then eventually this this happened. But then I do find, this, I try to, but it's inconclusive. Yeah, okay. I have to say, for the moment, inconclusive. I try to understand. There should be some deeper meaning to this sequence than what we know.
Because in the end, it feels like you have the start of the expansion of a very nonlinear function, and then you would get global existence, something like that.
Yes. Yeah. It's this. I think this sequence is interesting, right? It has it's at least interesting for me. Okay. So I think I like it. Yeah, because it is something very symmetric, right? It's symmetric. It is. I try to say it's telling me something, but I haven't figured out. I have to say, so I cannot report on this. Yeah, I tried for some time. I tried to make use of it, and I think, but I'm too. I don't know enough to just get more out of it. Yes.
Are there other questions?
Yeah. So because you give so precise constants in inequalities, do you expect to have kind of an optimal guy, or there is a bad guy?
Yes, that's also one of the motivation. Yeah, I think everything's very precise, and you can really get some, because it's equality, right? You are not give, it's precise equality. But unfortunately, I haven't been able to get something conclusive.
Not even in terms of self-similar solutions?
No.
Because everything is scaling invariant, so I guess there is the question if you expect these logarithmic spirals are behind this problem or not?
Log spiral. But what do I have no log spiral, right? Okay. Yeah, no, but I think some years ago I had some self-similar solution for, but that solution is without gravity. And this one, gravity is definitely important. Okay. Because where does this one come from? This one is exactly the gravity. So what's not here is that quantity, like imaginary part of the commutator Z, TH, CT alpha disappeared. So the gravity term is here. So if there's no gravity, this whole thing just breaks down. So here, gravity is very important. And I try to think further, but for the moment, I'm thinking in a different direction. So you go. Maybe one day I will come back again. So, but I like your question, but unfortunately I have nothing to report. I think was some time ago I was thinking about it. I thought this I should try to make some use of this symmetric thing, right? But for the moment, I cannot get further from what I have told you. Yeah.
For the future, then.
Yeah.
I suggest we keep the other questions for the coffee break. So let's thank the speaker again.